Okay, salam alaikum, shabab. Welcome back to the classroom. I received too many questions, of course, and I have been almost been busy all my office hours during the past days. And by the way, I would like to remind you about something. I have noticed that some students come to the office hour and they stayed in the waiting and then they disappear. And the reason why sometimes I cannot admit them is because I am consulting a student on a private matter. So what did I do? Sometimes I admit them and I ask them gently to leave the room and then come back again. But then they come back again and they stay waiting and then they go. So I want you to know that I have no other choice. I can't hold you multiple people at the same time and, you know, make somebody quiet and doesn't hear anything, and so, you know, I can't silence you. So please, if you come in to the office hour and I did not admit you, you see the meeting is going, but I didn't admit you, you should know that there is a reason. It's not because I am not around or I left my computer and I am no longer available. No, that's not the reason. So I hope you understand this. Now, the other part is about the project. Many of you are confused, which is very fine. And many of you ask me to like walk over the project. And listen, I am going to try my best, okay, to start solving this problem today. And I am pretty sure with a huge percentage, like 80 to 90%, you will understand the project based on this problem that you see now. Because basically it is the same. Design of shafts is always the same. And this is a good example. Now, I know that some of you are confused because there are more inputs, there are more information maybe in the project than what you need, which is very natural. And maybe you are confused with all of these forces and moments. But let's see. I am gonna go over this with you now, and let's see what is gonna happen. Okay. I am gonna try my best to comment on the points that you will probably face in the project. So this is something I promise to do. Now, here, what do we have? We have a double reduction gearbox design has to be developed to the point that the general layout and axial dimension of the counter shaft carrying 2 spur gears has been proposed. So this is a layout, and the layout was proposed. In your case, you have to make a layout. The gear and bearing are located, and of course, the purpose of the gears is transmit power. And what has been given to you, this is the idea. The tangential, look, this is, these two are the tangential and the radial forces generated because of the gear. Why? Because spur gears are the kind of gear that have a tooth like this. Of course, they have too many teeth. But when the other gear come and engage with them, the other gear will have its tooth like this. So there it is. And now what happened is that usually they come and touch at an angle. Okay, this angle is inclined by 20 degrees. Okay, this is usually 20 degrees is the pressure angle, we call it, for gears. I know you don't know this, you will know it when you take 308, but that's fine. It is explained, this pressure angle. If you go and search for it, you will understand it. Those who ask me, I explain it to them. Now, what are the consequences of this? The following is that we represent the gear like this with a single force acting at an angle 20, and we know that this is going to make a force here which is tangent to the gear, and that's why we call it tangential, and this one like this which is acting along the radius, so that's why we call it radial force. Now, what is important about these forces is that the shaft which is carrying the gear is now going in the screen, right? So the radial force, indeed, if you look at the gear like this, the radial force is actually applied like this, which means it is trying to bend the gear. No, sorry, the shaft. But the tangential force is acting out of the plane along the tangent. That's the one which is responsible for the torque. So if you know what is the torque which is acting along this gear, the shaft, the torque يا شباب is basically, it's the game. Power equal to T omega. The game here, I explained it to you one time. لما كنا نتكلم عن تعشق السيارة في الجير الثقيل ولا خفيف وتروح تطعس، صح ولا لا؟ So what did we say? We said that the power, the horsepower of the car is the same. خلاص لما يقول لك السيارة فيها 450 horsepower. So what, I don't know what is it, how much is it equivalent in watt, but in your turbine you have 500,000 watt, and then you know that the RPM of the shaft is given to you, which is in radian per second in here. Then you will end up knowing what is the torque. Now, if you know the torque, which is for the turbine, given to you, it's given. If you take the power and you take the RPM in radian per second and calculate the torque, it will be similar to the rotor torque, very close. So the rotor torque was given to you. Similar here, the torque is kind of known, or you know the tangential forces, and that's how you calculate the torque. It's either way. But the concept is this: if you know the torque T is related to the tangential force, so it is F tangent multiplied by the radius. Now, the radius here, sometimes it is known, sometimes it is not known. So, and of course, most of the time, like in your project, you don't know what is that force. You know that you should multiply cosine 20 by the force to get the tangential force, but you don't know that force. So in your case, for example, you know the torque, and you want to find that force. If you find F tangential, you can find F radial. And if you know the tangential force and you know the radial force, you know what are the forces, and you can draw the shear force diagram, and you can draw the bending moment diagram. So the idea here that students are facing with the project is the torque is known. They want to find Ft, but they don't know R. Now let's go to this problem and let's see what are the tricks to estimate diameters. Very rough estimate, sometimes very accurate, not too far from the actual one. So let me show you. So here, والله يا يوسف انت ما ادري وش سالفتك. لا هذا يوسف got in. This is another one. Okay, sorry. So we have two gears, and we have been given the tangential forces in this problem and the radial forces. Understood? Now, so what do we want? We want to make the design. We want to maintain a factor of safety of 1.5. And now let me show you the layout. Now, some student doesn't know what is a layout, and they were very upset. شلون يعني وشلون نسويها هذا? In a simple, يا شباب, in a simple way, I want you to understand that there might be many practical reasons why shafts are usually stepped. واحنا تكلمنا عنه في الانترودكشن last lecture that usually shaft that transmit power are stepped shaft or stepped cylinders. Steps معناها فيها step 1 2 3. As you see over here, this is our first step. Then there is another one. Then there is another one. Then there is a step. بعدين نزلنا تحت. بعدين نزلنا. بعدين نزلنا. Those are the steps. Why? Well, I am gonna tell you why. First, number one, steps are very, very practical way to locate element in exact position. So for example, if you want to dismantle the shaft, what do you need to do? You need to take off the bearings, you need to take off the gear and the other gear and the bearing. You take them off. But as you see, you cannot push the bearing in this direction to take it off. You can push it in this direction. Why? Because to the left, the diameter is getting bigger. You should push it toward the diameter where it gets smaller. Same thing, the gear and the bearing here has to be pushed to the left. Now what happened? You go and buy a new bearing, a new gear. Now you want to install them in. Then what do? Those machines are very precise. And you can easily misalign, put the bearing a little bit to the right, put the bearing or the gear a little bit to the left, and this will cause you problem. So one way to make sure that these elements are located exactly in the right place is through shoulders. So for example, تيجي انت شو تسوي؟ تبدأ بالgear صح؟ If you put the bearing, you will not be able to put the gear. So first تبدأ بالgear. تيجي وتاخذ الgear and then you slide it all the way until it hit the edge here. Do you see it? I am marking it. And now, boom, that's the gear in its perfect place. Perfect place. Then you slide the bearing until it hits that step. Same thing here, same thing there. A very simple argument. I don't need to explain any other one. Good. Now, this, of course, will introduce what? Will introduce diameters. طبعا in this shaft لو تلاحظون إنه اللي صاير هنا this way, over here, there it is. This is a location of a ring. So as you see, that little step over here, okay, is gonna cause a problem, stress concentration, and you will see that the stress concentration in this location is not little, is a lot. It might reach to 4 or something, but it is required. يقول لك أنا مثلا أبقى أحط ceiling, I want to install, you know, whatever, something needs to be put there. It is part of the operation. It has to go there. I have no choice. I have to design it. Is it going to increase the stress? So what? I will improve my design. I will make the diameter bigger. This is what the guys need. I can't say no. And of course, the dimensions as length are given. The most important thing to know is that they always put a datum. Practically, this is very important when you graduate one day. They put a datum and they measure all the dimensions from that datum. Do you know why? Because they don't want to accumulate error. ما تجي هنا وتسوي غلطة 0.01 بعدين هذا يصير فيه 0.01 وشوية زيادة. And then in here, you end up having an error of 1 millimeter. 1 millimeter in the industry is huge. I told you once that they treat these machines so carefully that their clearances are measured in thousands, 1/1000 of an inch. So you can't mess things up. Okay, good. Now the dimensions are given. In your case, the dimensions were not given. So you have only one gear, you have two bearings, I'm gonna leave it on you. You know, the length is 4 meters. والله تقول أنا بحط bearing على بعد متر, بعدين I leave 2 meters and then I put another bearing and then I put another gear. This is gonna play a lot with your bending and shear, and you will see the consequences. I don't think, يعني, you can do whatever you want with it, but the most important thing is you have to understand that you need to give yourself space. يعني ما ينفع تيجي تحط البيرنج وجنبه على طول الجير. Practically this doesn't work. And not only this, you may end up in real life having a bearing which is this big or that big, and the gear may be this wide. So you need to give yourself spaces, and you don't know these things yet. So just give yourself space, a meter, half a meter in between, just to make sure that your element will fit comfortably within the design. Now, once you have the torque given to you, you have the forces as weight in the design, and all what you need to do is to put them into right place. You know that bearings will cause reactions, normal and radial. Well, be careful يا شباب. When you have a gear, look at the gear. The radial force is acting downward in what? This is Y plane, this is Z plane, and this is the X plane. Now, the radial forces appears in the Y-X plane. This is radial force, this is another radial force, and of course, the bearing will react, and that's why you will have a reaction for bearing 1, a reaction for bearing 2, and so on. But who is going to handle these forces? The one that act in the Z direction, the bearing. So if you look at the bearing, when it holds the shaft, it can carry forces which are in this direction, and it can carry forces which are in this direction. So that's why you will end up solving the problem in two different planes. Y-X plane, Z-X plane. I hope this is very clear. Now, so if you look here, look, ya shabab, look at this bearing. Now, what did we have here? We have, this is the bearing here, bearing B, and this is bearing A. And in here, look, this is the reaction for the bearing, and this is the reaction of the bearing, and then this is the reaction of the other bearing. طبعا يا شباب انتم شو تلاحظون الreactions regardless of the direction of the forces, since they are unknown, it's better to assume them to act in the positive direction. Just convention. Later you will know if they are positive or negative. And of course you have the applied forces resulting from the tangential and the normal force because of the gear. Now, look what happened. With respect to the torque is, as I said, when the gears engaged, everyone is trying to push on the other, and the tangential force will be generated. So if you look at the shaft, the first free body diagram that you can draw, or the force diagram, is the torque diagram. This is the beginning of the shaft, and this is the end of the shaft. From the beginning, nothing is going on with respect to torque. Once you reach the gear, there it is, boom, you have a torque. Why? Because now you have a tangential force on this gear multiply by the radius of the gear. So that tangential force multiplied by the reaction by the radius, which is the torque, will reach to its maximum in the gear, and then it will continue. Why? There is no opposite torque until you reach the other gear. The other gear will act in the opposite way. And now, since this one is tangential force is going in this direction, the other one tangential force will go in the other direction, and this one will have a clockwise, the other one will have counterclockwise, and that's why the torque diagram will drop down at this location, and then it will go to 0. Balanced. It's balanced. You cannot have a torque which is not balanced. Do you understand? In your case, the rotor will apply the torque, will cause the torque to rotate, to be generated, 395,000 Newton meter, and then it will go the same until you reach the gear. And then there is a generator there. Now the generator will oppose the torque, will drop it to 0. So the torque will go from the maximum value all the way until the gear, and then it will drop. Which means torque, shabab, is always like this, straight. You just need to know where it starts and where it ends. This is very important. Why? Why? I'm going to tell you why here. Now, when we solve the problem, you will notice that if we design point K over here, point K, if you look down, there is no torque. So if you solve point K, if you design point K, you don't have a tau equals to 16t divided by d cube, whatever. ما في torque. But if you design point I or point J or point G, you have to have a torque. You have to have a shear stress. So that's something you need to worry about. Okay. Now, what happened is, since we know the forces over here, we can determine the reactions. طبعا يا شباب لما تسوون الreactions, how do you determine them? You take two planes, huh? You sum up the forces along the y direction. And then you sum up the forces along the z direction. And then you, in this plane, which is the y-x plane, you need also to sum the moment. About what? About the z. And this one, the z-x plane, you will sum up the forces along the z direction, and you will sum up the moment along the y. These two equations will help you to find the reaction in this plane. These two equations will help you find the reaction. It is determined problem. You shouldn't have indeterminate problem. Do you understand? So the reactions are all determined. And as I told you, the torque can be determined from the tangential force multiplied by the diameter over 2, which is equal to 540 multiplied by 12 over 2, and this is the torque. Now, listen to me carefully. The torque will be the same and the diameter of the gears are different. So what happened? You will see that in the other gear, if you calculate the torque by the other gear, the diameter is different, the tangential force is different, but you will end up getting the same value. You should get the same value. Okay? All right. Now, نجي للموضوع الأهم وهو once you draw the free body diagram in the X and Y plane, in the X and Z plane, then you start drawing the shear force diagram for each plane. So this is for XZ plane. XZ plane means we're talking about this plane and this one. So I am gonna just highlight this plane with the maybe, I don't know, maybe yellow. This plane, ya shabab. All right, this plane. So what happened right now? Just to know that this is the plane. We draw the free body diagram, the shear force diagram. This is the 0, okay? And this is the y-axis, and this is V. So what do we have? We have, let me highlight it maybe in blue. So this is 115, then it jumped to 655, and then it dropped down to minus 1,776, and then it goes up 0. We know that it has to end at 0. Means that our forces are balanced. So from the shear force diagram, we all know that we can get the bending moment diagram. And you will see that for most part, we have a straight lines in the shear force diagram, and we will have a linear lines in the bending, no distributed load, it will not be second order, and so on. Very straightforward. So what are you gonna get here? And remember that when you draw these diagrams, okay, they will tell you, they will help you identify the point. طبعا يا شباب زي ما انتم شايفين in this problem the point were actually predetermined. How would somebody decide which point are more likely to be analyzed? Well, very simple يا شباب. رقم واحد, first thing, we know that in order to mount gears, we need a key. Key will raise the stress. Is that true? So the location of the gears has to be analyzed. There is a stress concentration factor. There is a big risk in there. Okay? Another thing, we need to look at the fillets. There's no doubt about it. And in this problem, because we have been given a returning ring, a location for a ring, which we will discuss in the solution, we also decided to take that point. So definitely now, in your problem, you will know that the location of the bearing, the location of the shoulder, the location of the gears has to be analyzed. Another thing is that when you draw the shear force and bending moment diagram, you will also recognize the points which are also risky, or point where the bending moment diagram is high. So once you draw the free body diagram, you will know what are the points, what are the cross-section that you will likely to analyze. What you need to understand is this, ya shabab. Be careful. There are locations where the moment may not be too high, but because there is a stress concentration. لاحظوا يا شباب, المومنت والشير فورس ما لها شغل بالstress concentration. It doesn't have to do anything with it. The stress will be affected by it. And that's why, be careful. Even if the bending moment, look, you don't just analyze one point here, the maximum. You have to look at other points, especially the ones at the stress concentration factor. Now look, let's move on. You see how interesting things are getting. We're gonna go now to the other plane, which is what? The YX plane, which is this plane. This plane, the one facing you right now. So what did we do? We got the reaction. From the reactions, we draw the shear force diagram like this. And then we go to what? The bending moment diagram. This is the bending moment diagram. And of course, this doesn't change anything right now. We are targeting the same point on both planes. ما يفرق. Why? This is something very simple, but I am pretty sure since you did not do it, you will think it is new, but it is not. This is what will happen next. Do you see? I want you to look carefully. Do you see this equation? This equation is the resultant bending moment. Why? Because, ya akhwan, this is what happened. When you have a bending moment acting in this plane, this is YX, and then another bending moment acting in the, for example, in the ZX plane, it means, ya shabab, that somewhere in between you will have the maximum. يعني معناها إنه the cross section when it is like this, okay, if you look at it from the side, you may have bending like this. Okay, why? This bending is coming from this plane, and you have another bending coming in this plane. I'm gonna draw it maybe with red. Do you see that? Now things are in between. And just think about it this way. If you have a moment in the y-x plane and you have a moment in the z-x plane, then the resultant moment will be equal to the moment of y-x square plus the moment of z-x square. Yeah. Now what will happen? You might end up with a moment which is oriented this way. يعني كيف الماكسيمum is coming like this and then like this at an angle, not horizontal, not vertical, no, at an angle. You don't care about the angle. Why? Because we will always focus on these maximum points. But how do you do it? You go, as I said, you go, now look, this one is the total moment diagram. طبعا التركيز على moment diagram. You understand that? Because it's the trouble. Remember, the shear force diagram, we are not going to use it based on our theory. We said we don't want to use it. So we will talk, torque diagram is one, very simple, straight. The bending moment diagram, we need one diagram, not two. So how do I do it? I go here, I take this point, and then I take this point, and what do? I square them under the square root. And what do I get? I get this new point over here. This point is the square root of my square plus myx and mzx squared under the square root, the resultant, ya shabab. So now I am very happy. I got one bending moment diagram and I got one little tiny torque diagram. خلاص خلصنا. It's over now. Moments I have it, and I know the torque. The torque, if you remember, was like this. It was coming 0, up, then 0, and that's it. خلاص انتهينا. الآن أنا أجي نقطة نقطة, point, and I take the point. Does it have a moment? Does it have a torque? Does it have a mean? Does it have an amplitude? And so on. So let me show you how. Now, how do you know if the moments are means or amplitudes? In your design project, we gave you those. We gave you maximum and minimum. So you can find the resultant moment maximum at, for the resultant from two plane, and you can find the resultant minimum, and then you can calculate the amplitude moment and calculate the mean moment. That's very simple, right? But don't forget that when you take the resultant, you need to take one at one plane, the other one at the other plane, you square them, you put them under the square root, and then you add them. Here, we don't have this. We don't have minimum and maximum. We were given forces. So let me tell you how in this problem we analyzed which one is mean, which one is amplitude. So for the moment, ya shabab, what happened? If you have been given a moment and the shaft is rotating, then this is like a rotating bending problem. In rotating bending problem, there is a moment which is trying to bend the beam, and the beam is rotating. When the beam rotates, automatically you will have a completely reversed bending. The moment that are here are actually amplitude, and there is no mean because it's completely reversed. That's it. But in your problem, we gave you a minimum and maximum, which we are trying to tell you It is not completely reversed. There are things that are reversed. There are things that may not be. So that's why we have some means and amplitude. How about the torque? The torque, ya shabab, look what happened. For the torque, when the shaft rotates, the torque is always applied. And if you look at the shaft, when you apply the torque, all points on the top are always at the maximum shear. So even though you rotate the shaft, those points are still always under the maximum shear, which means the value of the torque is always there. If it is always there, it means it's the mean. It's a static value. It's not an amplitude. That's why the torque is always mean in this problem, مو في project, and the moment is always amplitude. Again, in this problem. Now, is the torque gonna cause a mean and amplitude? That's for you to think about. It's very similar. But this is the idea why we have a mean moment which is equals to 0 and a torque amplitude which is equals to 0 in this problem. Okay? Now, if we know now this, look what is going to happen. Now, in the book, ya shabab, the chapter, there is a lot of reading materials that will give you a very, very, very important and key assumptions for designing a shaft. From where we brought these assumptions? We brought them from experience. يعني مثلا أنا قلت لكم لما تكلمنا عن how do we integrate von Mises distortion energy with Goodman or with Gerber. I told you when you calculate the equation for D, it's inside it, it has KF, but we don't know KF because we don't know the diameter. This is what I told you. Now look what I'm going to show you. I want you to look down in the bottom of the slide, ya shabab. I know the table is very little and tiny, and maybe in the slide, hopefully I will not ruin it. I will try to enlarge it for you, okay? Is it coming up? Okay, oh yeah, all right, good. So what does this say? It says that the first estimate for what? For the fatigue, for the stress concentration factor KT. For what? For shoulder fillet, look, shoulder fillet, and it is sharp. If it is sharp, KT for bending is 2.7, KT for torsion is 2.2, and KT for axial is equals to 3. What if it is round, well rounded? يعني معناها يا شباب إنه الفلت, if it is sharp, it is like this. If it is well rounded, then it is like that. So if it is well rounded, this is 1.7, 1.5, and 1.9. Now remember, this is KT without the need to know the diameter. This is very beautiful. خلاص, if you find KT, what should you do now? You say, I will subtract 1, multiply it by Q, and then KF equals to 1 plus. Now, باقي تحدي واحد. What is a Q? In order to find the Q, I need R. And what is this? What is the radius here? I don't know. So we'll show you how we get away with that. But these one are, you see, the end mill key seat. And this is a key seat for sled runner, and this for a returning ring groove. Those are the first assumption KTs. يعني مو تروح تحط لي KT من عندك دماغك and تقول خليني أجرب. Is it gonna work or not? I don't know. No. Getting a good estimate will always make you reach the solution faster. We know, ya shabab, that you will have to do iteration, but we want to minimize those number of iterations, okay? So what are we going to do right now is this. I'm fixing this again. Okay, I'm not gonna spend the whole lecture trying to be perfect over here. So what's gonna happen is the following. Look, we are going to assume a generous fillet radius for the gear at I location, okay? And from that, we're gonna go to table 7.1, which is this table, and we'll find that KT for bending is 1.7 and KTS for shear is 1.5 because we assumed a generous fillet and we need only torsion and bending. We don't care about axial. Okay. Now look, yes, about this is a key point. For a conservative first assumption, we are going to assume that KF equals to KT and KFS equals to KTS. Why it is conservative؟ رقم واحد، احنا قلنا في that when you calculate KF, it is 1 plus Q multiplied by KT minus 1. Clearly the equation here, we will take KT, راح نطرح منه واحد، بعدين نضربه في Q. Q is less than 1, and then we will add 1. So what is the result? If KT is equal to 2.1, KF might be 1.8. So 1.8 will not amplify the stress like 2.1. But why not? أنا الآن متحفظ، خايف. Let me be conservative. Being conservative, I assume that KT equals to KF because usually KF is less than KT. So if I use KT equals to KF equals to KT, أنا يعني قاعد الآن أسوي design safer. Do you understand? So there you go. We got rid of KF and KFS. That's very huge. And now what is the next step? Is to assume a material. So in this problem, the book says we will choose inexpensive steel. أنا قلت لكم من قبل, if you use high number steel, it will be more expensive. So we also told you in the slide in the previous lecture that usually people use 1020 up to 1050. So, and it is either cold drawn or hot rolled. So in here we use 1020 cold drawn. Once we know this, what do we know? We know SUT, we know SY. If we know SUT, we can find SA prime. Is that right? So we got SUT, and from SUT we can calculate SE. Now, there are a few assumptions here. First of all, what is Ka, the surface factor? It's very simple. I know SUT, and because it is cold drawn, I can find A and B. And this is it. I calculated it. This one has no assumption. No assumption. I calculated exactly as it's supposed to be. Now, what is KB? Do you remember KB, ya shabab? It's the size factor. And we have bending and torsion together. So size factor is not 1. Size factor is 1 when we use a steel. So what is a good assumption? خلاص يا شباب, you don't need to think about it. The first assumption for KB, reasonable good assumption for KB, is 0.9. خلاص, use it. First assumption, KB is 0.9. What is KC? What is KD? What is KE? All of them are close to 1. What did I do? I just calculated SE, the fully corrected endurance limit. When I calculate the fully corrected endurance limit, and I know SUT, and I know KF, and I know KFS, خلاص خلصنا. باقي شيء واحد. The problem says the factor of safety is 1.5. So what I'm going to do? I'm going to use the equation for the diameter with Goodman. Okay? Why? Goodman equation is very simple. If the problem doesn't mandate as elliptic or Gerber, why should I use them? Let me use Goodman. Goodman is simple. And I use Goodman, and congratulations, Shabab. You got the diameter. One diameter will solve everything. Everything. Do you understand? You will see it. هذه يا شباب زي المصباح زي الحلقة. Once you unfold it, everything fall down. This first diameter, just find it. Go and pick a point where you know the torque, and you can assume that yielding, estimate the diameter based on yielding, estimate the diameter based on fatigue, based on just give yourself a diameter. But when you get a diameter, don't make it out of your head. Make it out of a simple equation. تقول أنا بروح عند النهاية هنا. There is only torque, there is no bending. Then I will use the torque equation, and I find the shear, and then I will equate the shear with yielding. For example, boom, you get the first diameter. That diameter will not be right, but it's a very good estimate. And you will see the end diameter will not be far from it. Okay, now look, we found the first diameter. We are running out of time. Now what happened? We said, okay, كل الassumption اللي سويناها were conservative. So now let's clean them up. The first cleaning process يا شباب إنه if you go at the back of your book, okay, the back of your book, there is a table for sizes. It's called prefer sizes, and it is table A17 in my version. It's over there, and it gives you the prefer sizes for millimeter and inches. What does this mean? It means يا شباب إنه الديامتر اللي حسبناه, okay, the diameter 1.65 is not preferred. يعني إيش معناها؟ يعني لو بقينا نحط عليه bearing, I will not find a bearing that fits 1.65. If I want to put a gear on it, I will not find. What would I find? I will find a preferred size. So what did I do? I go to the book and I try to look for 1.65. I didn't find 1.65. What I found, now I'm going to tell you, there is 1.6, or there is 1.8, and I think, no, this is not it. I think I have a different, oh, this is for millimeter, sorry. There is 1.6 inches or 1.4, and I think there is a problem in my book over here. So what happened, ya shabab, is that based on the solution, they found that the next preferred size is not 1.65, is 1.625. Why did the solution in the book used a lower value, not a higher value? قال لك لأنه أنا already كنت عامل very conservative assumption. So if there is no 1.65, I don't need to go up, let me go lower. So when you change the diameter, what happened right now? If you change if you decide that the diameter is 1.625, you need to go solve everything with the diameter known. So you can find KT now, KF, you can find KB. You don't need to assume it's 0.9. You can actually calculate it. So this is what we are going to do next class. Don't be surprised. This problem, if we finish it in 2 classes, it will be really great. And I hope, ya shabab, by this time, you know what to do with the project. I hope so. So I'm going to switch off my webcam, and I am going to share my screen, and I hope that everybody will turn on their webcam quickly. We take that in 1 minute. By the way, shabab, before you leave, I have a meeting today during my office hour. So I scheduled it after this class. I know it may not be convenient for many of you, but I'm sorry, I have no other choice. In the afternoon, I have too many meetings. So this is the only time. Faisal?
Yes.
You can leave. Yusuf?
Here.
Hamad?
Yes.
Ali?
Yes.
Yusuf?
Yes.
Majid?
Yes.
Hussein?
Yes.
Muhammad?
Yes.
Hassan?
Yes. Yes.
Mubarak?
Yes, دكتور.
أحمد.
Yes.
Okay. Ali. Haji. Ali, where are you? I think I saw
دكتور
you.
مبارك يا دكتور.
Yes. Where are you, Mubarak?
قاعد أحاول أفتح المايك ما يشتغل.
Where is Ali? معجب.
Yes.
سلطان.
Yes دكتور.
عبد الله.
Yes.
سلطان.
Yes.
عبد الرحمن.
Yes.
خالد عتيبي.
Yes, دكتور.
عبد الله العوفي. عبد الله. فارس قحطاني.
Yes.
ثابت.
Yes, دكتور.
علي رمضان.
Yes, دكتور.
اوكي. هاشم.
Yes.
ماجد.
Yes.
محمد.
Yes, دكتور.
احمد.
Yes,
سلطان.
دكتور.
مشعل يامي. مشعل. وليد.
Yes, دكتور.
محمد.
Yes دكتور موجود.
عبد الله.
Yes, دكتور.
and أحمد.
Yes, دكتور.
اوكي. ثانك يو يا شباب.
دكتور أنا من السكشن الثاني دكتور.
Just wait a second. Let me find you.
Okay.
Where are you? I'm gonna put you excused and then I will change it later today. What is your name?
سعد محزمة.
سعد.
In the middle دكتور. Yes.
Okay. Okay.
Thank you دكتور.
Welcome. يلا يا شباب. If you need anything, you'll see me in my office hour in 8 minutes.